Interrealtion between geometric ratios of steel chimney and deflection by static and dynamic analysis. Abstract A. Most of the industrial steel chimneys are tall structures with circular cross-section. Tall chimney plays pivotal role in proper functioning of most of industrial facilities. In this thesis we are considering chimney used for dedusting system. The basic dimension of industrial self-supporting steel chimneys such as height, diameter at entry, diameter at exit, etc. are taken hypothetically for the study purpose. For comparison analysis, area is proposed for the design of structural self-supporting steel chimney at Indore, plain terrain, certain terrain conditions. Wind pressure is calculated as per is 875, part 3, and maximum bending moment and stress for all the chimneys were calculated by using the MS Excel sheet.For static wind load calculations. Reference is made of design of steel structure by Dr.B.C Punmia and dynamic wind load calculation as per the procedure given in IS 6533, 1989, part 2. By comparing the three design results like self-supporting chimney stresses, thickness of shells, an effort has been made to arrive at possible/probable cost-effective recommendation toward design parameters. Keywords: A self-supporting chimney, height 75 m, of different top and bottom diameter, static wind pressure, dynamic wind pressure, structural design, mode shape, sheet.For, deflection. Introduction. Chimneys or stacks are very important industrial structures for emitting toxic gases to a height of so that the gases do not contaminate the surrounding atmosphere. These structures are tall, slender, and generally with circular cross-sections. Different building materials, such as concrete, steel or masonry, are used to build chimneys. Steel chimneys are ideal for process jobs where a short warm-up period and low thermal capacity are required. In addition, the steel chimneys are economical for heights up to 45 m. With large-scale industrial developments taking place everywhere, a large number of tall chimneys would need to be built every year. Building chimneys this tall requires a better understanding of the loads acting on them and their structure. Proper design and construction of such chimneys creates self-contained structures that can withstand wind loads and other forces acting on them. Chimneys are more susceptible to wind and earthquake loads, which can cause serious problems in power plants and large industries. Numerous standards are available for the construction of self-supporting industrial steel chimneys, one of which is Indian standard is 6533, 1989, Part 1 and Part 2. The geometry of a self-supporting steel chimney plays an important role in its structural behavior under dynamic lateral loading. This is because the geometry is mainly responsible for the stiffness of the chimney. Some basic geometrical parameters of the steel chimney, e.g. total height, diameter at the exit, etc., they are associated with the corresponding environmental conditions. In addition to that design code, IS 6533, 1989 Part 2, several criteria are imposed on the geometry of steel chimneys to ensure a desired failure mode. Two important geometric consideration form IS 6533, 1989 Part 2 are: the minimum outside diameter of the unlined chimney at the top should be 1/20th of the height of the cylindrical section of the chimney. The minimum outside diameter of the flared chimney without lining at the base must be 1.6 the outside diameter of the chimney at the top. Present study attempt to relate the geometric ratios and the deflection of steel chimney using sheet.For. Software and manual calculation using MS Excel. 2. Objective of study: to study the effect of wind loads on the structure and to determine the loads that are more effective on the dynamic behavior of the structure. Study will be more focused on the deflection of the tall chimney due to wind and earthquake, and the analysis done will be the dynamic analysis and the static analysis. Deflection is also the governing factor for the tall structure. Depending upon the type of structure there are different permissible value of deflection, thus study will keep deflection in permissible limits for all the diameters considered. The objective of current study also the aspects influence of tall chimney design. Hundreds are calculated as per code is 4998, Part 1 1992. The analysis is done using the STD-PRO. The deflections area unit determined and checked whether or not the area unit below the limiting worth as mentioned within the code. A complete of 8 models with totally different slopes area unit generated and analyzed. The deflections and stresses at various levels area unit determined and therefore the best slope combination that provides least deflection is terminated. G.Murali, B.Mohan, P.Sitara, P.Jayashri, 2012, Response of mild steel chimney under wind loads. This paper deals with the analysis of 3 chimney of 5 m height and designed as per IS 6533-1989 and wind masses were calculated as per IS 875-19872. The wind speed thought about were 47 m/s, 50 m/s, 55 m/s and also the static force, dynamic forces, static moment, and thickness of those chimney shells are compared. Kalpishthoput, Sri Rang Tand, Abhijit und Hakar, 2018, Analysis of self-supported steel chimney with the effects of geometrical parameters. 49 Range of steel chimney. 7 Totally different height and high diameter area unit handpicked and analyzed for wind loading and seismal loading as per IS 6533-2 and IS 1893-4 and analyzed by mistreatment. The finite part software package STAA Professional VI8 and MS Surpass. The investigation has been distributed. The variation of parameter in impact of height to base diameter magnitude relation and height to base diameter magnitude relation. Literature survey. Kirtikanta Saho, 2012, Analysis of self-supported steel chimney as per Indian standard. The target of this paper is to justify the code criteria with relevancy. Basic dimension of commercial steel chimney. A total of 66 variety independent steel flaring unlined chimneys with totally different top to base diameter magnitude relation and height to base diameter ratios were thought of for this study. The thickness of the chimney was unbroken constant for all the cases. Most bending moment and stress for all the chimneys were calculated for the dynamic wind load as per the procedure given in IS 6533, 1989, Part 2. Victimization MathCAD software package. Also, the results were verified with finite component analysis victimization business package and SIT. Chaitanya Bharata Prasad, Dr. K. L. Radhika, Mrs. P. Anuradha, B. Santosh Reddy, 2018, Dynamic analysis of a tall chimney. The target of this paper confirmed that masses are predominant on the structure and to seek out the slope that generates the smallest amount deflection for a chimney height of 310 m. The cross-section area, bottom diameter, and thickness of the chimney is maintained same. The Professor Uday Singh Patil, Professor Devendra Patali, 2018, Static and dynamic analysis of steel chimneys using different codes. Different cross-section of the chimney has been thought about and analyzed for the wind load. Each static and dynamic analysis had been performed of the chimney. Comparative study has been done by mistreatment typical methodology with the static moment obtained by IS 6533 half a pair of equally the dynamic moment at the bottom of the steel chimney square measure compared considering IS 6533 PART2, as/NZS, 1170.2, 2002. And DDENV 1991-2A4, 1995. Mr. Praveen Kumar, Dr. A.J. Swarup, 2016. Analysis of self-supporting steel chimney. The effects of lateral force because of wind and earthquake masses square measure analyzed by the same static load methodology and dynamic analysis by response spectrum methodology. The region has been considered of Nashik and tract class has been thought about consequently. The wind load and earthquake parameter were thought about as per IS 1893-4 and 875 Part 3. Methodology. For a comparative analysis, a steel chimney has been considered. To achieve the objective, following step-by-step procedures are followed. Carry out literature study to find out the objectives of the project work. Select chimney geometry for all the 3 locations. Calculate the loading on chimney and load combinations. A study on the various parts of a chimney. Understand the procedure of design of a steel chimney as per is 6533:1989. Select various points and following the various limitations as per the Indian Standard Code. Analyses and design using sheet.For and Excel sheet calculation for 5 different geometries and compare deflection chimneys with different geometric ratios. Modeling and problem formulation. In the present study, a steel chimney of 80 m height subjected to the wind loads imposed due to the mean hourly wind speed of 39 m/sec in the seismic zone 3 is considered for the analysis. Single flue of structural steel is provided to discharge the flue gases. The shell rests on RCC mat foundation of circular shape. The following are the details of the chimney considered. Unit weight of steel A 78.5 kN/m3. Height of chimney A 75 m maximum outer diameter at bottom, A 6.5 m minimum outer diameter at top, A 2.0 m, min. Thickness of shell at bottom, A 24 mm. Thickness of shell at top, A 20 mm. Grade of steel A Fe 250. Basic wind speed A 39 m/sec. Base A rigid. Seismic zone A3. Damping ratio A 5%. Geometric variation A top dia to height ratio, bottom dia to height ratio. Calculation of wind load and moment will be done using IS 875-2015, Part 3, and IS 6533-1989, Part 2. 4.1 Loading conditions. Loading line diagram in sheet.For is as shown below for static loading and dynamic loading for all 5 model. Live loads, as per is, 875, Part 2, 1987. Wind load as per is 875 A 2015, Part 3. Load combinations. Comparative results. Percentage increase in load from static to dynamic. Results. It is observed that for Model 1 and 2 dynamic load more for higher elevation, but after height of 5 m it becomes less and become very less for lower elevations. It is observed that for Model 3, 4, and 5 dynamic load more for higher elevation, but after height of 5-6 m it becomes less and become very less for lower elevations. Conclusion. Percentage increase in dynamic force in more in chimney lower diameter as compared to chimney of higher diameter. Decrease in dynamic force in more significant from top to bottom as compared to static force. Dynamic force become lower than the static force for elevation below certain level from the top. Chimney with lesser diameter undergoes more deflation as compared to chimney of higher diameter. For same geometric ratio, deflection after applying dynamic load is more as compared to deflection after static analysis. Percentage increase in deflection after dynamic analysis is more for chimney of lower diameter as compared to chimney of higher diameter. For chimney of higher diameter, percentage change in deflection is less significant as compared to chimney of lower diameter. Future scope of work. To further study and incorporate the recommendation of Indian Standard Code, with regards to provision of instrumentation to the chimney at different levels, to continuously measure and monitor wind data. Location of stress concentration due to high temperature of flue gases, consequent crack originating/spread and the remedial additional design reinforcements. Discussion on flue opening, breach opening. Comparison between different types of foundation which are suitable for steel chimney with take care of wind effect and earthquake effect.